Hi, I'm Adam. Welcome back to Godot Gamedev. In this video, we'll take a look at the homing movement 2D component. Now, designing components can be as easy as asking three important questions. What is that one thing that the component does? What data is needed for the component to do its thing? And finally, how does it communicate with other components or the outside world in general? Now, what is that one thing that a homing movement 2D does? It moves and rotates its owner 2D node towards another target. Also, it uses a steering force model to simulate momentum and smooth the homing movement. Now, what data is needed for this component to do its thing? First of all, we'll need a target node 2D that this component will pursue. Then we'll have a maximum speed given in pixels per second. And finally, we'll have a variable called steer force, which defines the sharpness of turning. The higher the steer force, the more aggressive, the more instant the tracking becomes. Now, how does this component communicate with the outside world? Well, this component really does not need to communicate with the outside world. It handles the movement itself directly on the owner node in the physics process virtual method. If for some reason you need to communicate something like, let's say that a homing movement, for example, a homing missile is launched and you want to destroy it after n seconds, right? Then you can use a timer node for that. If you want to destroy it when it collides with an obstacle or collides with an enemy, again, you want to use an area 2D for that. So this component itself is just responsible for handling the movement, the homing behavior, as long as it's needed. For this, there's really no communication needed when we have our owner node which we want to move and the target that we can follow. Now let's see how we can implement this homing movement 2D component. We'll start by adding a custom icon to make it feel like this component is part of the Godot ecosystem, followed up by a custom class name called homing movement 2D, and making sure that the class itself is extended from the node class. Again, we don't need node 2D here because the owner itself needs to be a node 2D, so we can move it. Then we have a bunch of export variables. First, we have the target that we want to follow. It needs to be a node 2D as well. Then we have a speed variable, which is the maximum speed of the linear movement in pixels per second. And finally, we have that steer force variable, which defines the sharpness of turning. The higher value means more aggressive, more instant turning, and the lower values, like 5 is really low here, it means that the movement will steer very slowly towards the target, so it's more like a drifting kind of movement. Then we have a private member variable, hence the leading underscore, and for the current velocity of the owner's movement, this is a vector 2 and it defaults to 0. Now the interesting thing happens here in the ready. So what we want to do is we want to initialize the velocity. A good question is why. When we take a look at the example, I will show you the difference so it's easier to demonstrate. But one interesting thing that you can see here is we have owner.transform.x. Now what the heck is transform? And we'll take a quick detour here. So I really recommend this website. It's called Godot Recipes by Kids Can Code, and it's an awesome collection of useful things in Godot. And we have Gamedev math, and inside that we have transforms. So this is sort of like a blog post explaining how transforms work. I don't really want to get into detail. The thing we need to be aware of is that we have a 2D space inside Godot. It's its own coordinate system, the one we have. If we have an object inside it, it has its own x and y axes. And this is called transform. And it makes our life a hell of a lot easier because it explains that otherwise if we want to move this rocket ship forwards, meaning based on its own looking direction forwards, for that calculation to work, we would need some math like this. Compared to using sine and cosine for something like just moving it forwards, it's much easier to introduce this inner axis, so to speak, which is called the transform or the local axis. And we have that vector at all times that is pointing towards the forward direction of that rocket ship. And it's called the transform vector for all 2D objects in the 2D space. And the red axis is the x of the transform and the green one is the y. So we know the downwards and the forwards direction, but if we know them, then we know all the four directions, right? Because we can just multiply them by -1. So in this case, if we want the homing movement to not be jarring and instantly turn towards the target, we want the homing movement to start at the direction of the current forwards direction for the missile that we have, for example. So we want to use this red vector as the starting point of the movement and and then slowly it will steer towards its target, right? Again, we'll take a look at the example and it will make sense, but I just wanted to kind of show you what this transform vector is, and this image is an awesome example. If you want to read more on the transforms, it's super cool, condensed and useful blog post. I'll just leave the link in the description. So back to the code. We set the initial velocity to point towards the current rotation of the owner, the current forwards rotation of the owner, multiplied by the speed, right? So it moves at a constant speed. And then we move on to the movement itself. Again, inside physics process, we start with a safeguard. And what this safeguard does is it makes sure that we have a valid target. So if for whatever reason the target is being deleted or it's no longer valid inside the game, we don't need to follow anything, so we can return from this method immediately. Then we want to do the steering behavior. So first we calculate two vectors. One is called the desired vector. And if you take a look at it, it's a bit of a longer line of code. We grab the target's global position and subtract the owner's global position by it. With this, we get a vector that is pointing from the owner to the target in the shortest path possible. And what this means, it's called the desired vector because if we were moving straight at the fastest way towards the enemy, this would be the vector that we want to move on. So when we have that direction, we normalize the vector's length, so it will be 1, and we multiply it by the speed. So this basically gives us a vector that if we were to move in the most optimal way possible from the owner to the target, this would be the vector that we would use. But we actually don't want to do that, right? Because the steering behavior or this homing behavior wants to work in a way that it's not instant, because that would be very unfair for projectiles that we want to follow a target, right? In most games, we use this steering behavior to make it sure that over time, it kind of steers towards the target, but not instantly. Based on the desired vector and the current velocity that this target is moving towards, which again, we'll just start by the owner's current forward direction. So we take the difference between those two vectors, normalize it, and only multiply it with the steer force. And this way, we will have a steer vector that is kind of slowly moving towards that direction we want. And finally, how do we apply this to the velocity of the owner? Well, we just grab the current velocity that we have and we add the steer velocity that we calculated to it, multiplied by the delta to make sure that it stays frame rate independent. Now, with this, what can happen is that we end up with a longer length vector that would be possible based on our speed. Because if you remember, our speed variable is capped at 400. And it should move at a linear speed, right? So what we do is we call vector to that limit length and pass in the speed as a parameter. So when we add the steering to the velocity, if we were end up with a larger speed that we can move with, then we limit the length of the vector to that maximum speed that we have. But this just limits the length of it. The direction will steer towards the target slowly. And with that calculation out of the way, we have the velocity that we want to move the owner with. So what we do is we update its global position based on the velocity multiplied by the delta, again, to make sure it's frame rate independent. And we also want to update the rotation because with homing movements, you almost always want to rotate as well towards the target, right? So the steering behavior would look really weird if we were following a target but not rotate towards the direction that we are going. Okay, that was a bit of a longer one, but hopefully the description makes sense. Now let's take a look at it in action. If you like my content, please consider checking out my Ko-fi page where you can donate one time or become a member and get early access to all my content and videos. So I have the project open here and we have this example scene for homing movement 2D. It's a pretty basic scene setup. We have an area 2D enemy, so it can eat all the arrows. And this will be moved by code inside the homing movement, the root 2D. And we also have a character which has a couple of things attached to it. It has a sprite 2D and under that it has a weapon which is anchored to the center of the character. So when we rotate this weapon, you'll see that all child nodes will rotate around this pivot point, which makes it easy to aim with. And we have a couple of sprites, 2 hands, 1 bow, and we have a muzzle. And this is where we want to spawn the homing missiles. Here we have a bit of a problem because this is the position and the rotation where we want to spawn the homing arrow. But the problem with this is if we instantiate our homing movement arrow here, it will start moving, right? Something like this towards its target. But since it's added under the muzzle as a child node, if I were to rotate the weapon with my mouse aiming, this will also update the rotation and the position of the arrow itself. And we don't really want to do that. We want this arrow to be independent from its parent. So what we want to do is when we spawn it, we spawn at the position and the rotation of the muzzle, but not under the muzzle. So we can just copy these global rotation and position values from the muzzle, but also spawn the arrow independently. So now if it starts moving towards the target and I were to rotate the weapon, you'll see it no longer rotates with it because it's independent from it in the scene tree. This is something that we already tackled in the scene spawner component episode, but if you haven't watched it yet, I just wanted to demonstrate this problem, right? We need to be aware of that. And I don't use the scene spawner component here. You'll see there's no scene spawner inside because I want these tutorials to be self-contained. So if you were just watching this video, then you can still get a working example of the homing movement 2D. Now we also have a background and the disabled button just to sort of give you an instruction, and that's about it, right? It's a pretty straightforward, simple setup. Let's take a look at the code of the homing movement 2D root node. This is a bit of a longer code, but it's not that complicated. We have two export variables, one for the enemy speed, because for the homing movement to test it, we want the enemy to be moving, right? And we also have one export variable for the homing arrow scene that we want to instantiate. After that, we grab an already variable reference to the enemy node, so we can reference it in the script. And we have three private member variables. We want to store the enemy's starting position, the enemy's current target position, and the enemy's current velocity. What I did with the enemy behavior is just a simple wandering around script. It starts from a position that we provide in the editor, this position, and we can just imagine that we draw a rectangle around this enemy and it can move to random points inside this rectangle. That's the behavior that we want. Now inside ready, we set the starting position variable to the enemy's global position. So we store where the enemy started moving from, and we get a new random position or target position for the enemy to move towards. We'll take a look at the implementation of this method next. It's pretty basic. We just override the enemy target position variable based on the enemy start position, and we just add a random vector 2 to it so it can move randomly based on the 300 by 200 rectangle drawn around its starting position. Right? Let's move to process next to see how we move our enemy. So the enemy velocity at every frame will be the enemy's target position minus the enemy's global position that it currently has. This gives the simplest or shortest path between its global position and the target position. We normalize that vector to make sure it's limited to the unit vector length and multiplied by the enemy speed. So it moves at the speed that we defined as the export variable, and update the enemy's global position by adding that velocity times delta to it. And we check if we actually reached that random point that we had in mind, because we just say if enemy.global position.distance to, which is a vector 2 method, and take the enemy target position. We say that if this distance is less than 5 pixels, we are pretty close to reaching that point. So we just assign a new enemy position. So what this means for the enemy part of the script, if we run the scene, you'll see that it just randomly goes from place to place inside that imaginary rectangle based on its starting position. Maybe it's a bit too fast, but it works well with the example, right? I hand-coded this behavior, but I'm pretty sure along the line, we'll just do a component for this called Wander 2D or something like that. So enemies can wander around inside the rectangle. This behavior is super handy to turn into a component. But for now, we'll just coded it so it becomes self-contained for the homing movement 2D. Now, the final piece of code that we haven't looked at is handling input. The easier one is just mouse motion. So when we move the mouse around, we use the character's weapon, which is this node right here. And if you remember, when we rotated this, the whole bow and the muzzle and the hands rotate along with it around this pivot. So we basically rotate it to make sure that it points at or looks at the global mouse position that we currently have. Now this look at method, if we press and hold Ctrl and click on it, is defined for all node 2Ds. And what it does is it rotates the node so the local plus axis, which is the transform.x, points towards the point, which is expected to use global coordinates. And this is awesome because it means that the new forward direction for the weapon becomes the global mouse position's direction. And this results in running the script, and if I move the mouse around, the weapon just always points towards the mouse. So it's an easy way to do this mouse-based aiming. And what happens when we actually want to press fire to spawn a new homing movement 2D arrow? We instantiate that arrow scene that we have as an export variable and update its global rotation and global position based on the muzzle of the weapon. Again, if you watched the scene spawner video, the scene spawner component can do this on its own, and we would save a lot of lines of code, but we just did it by hand here, so everything stays self-contained. And finally, there's a bit of a spaghetti. I would never do it like this in a full project, but for these example scenes, I just want them to work as fast and dirty as possible to demonstrate how it works. I want the code to be clean and nice for the component itself, but not for the example scenes. So what I do here is I grab the new arrow node and call getNode. As a string, I pass in homing movement 2D. So if we really quickly switch over to the homing movement 2D arrow, it will grab this node based on the name of it, which is a terrible way to do it, because if I were to rename this to anything else, like just homing, then it wouldn't work anymore. So in a script, I would never do it like this, but this way I don't have to add code to the homing movement arrow scene itself. So what this does is it grabs the homing movement 2D node, and we know that it's a homing movement 2D component, and it has a target export variable, and we set it to the enemy. So the owner of the homing movement 2D component will chase this target, which is the enemy itself. And finally, when we have everything set up for the arrow, we just add it under getTree.currentScene to solve that problem of spawning it, right? So we don't want to spawn it under the muzzle, we want to spawn it under homing movement 2D or the root of the current scene. So it will become independent from the muzzle. It just copies its global position and rotation when we instantiate the arrow. Awesome, so that's all the setup we need for this to work. But before actually testing it, we can also take a look at the arrow scene itself. It's super simple. It doesn't even have any unique scripts attached to it. It's an area 2D with the layer set to 1 and the mask set to 2, so it can collide with the enemy. We have a sprite 2D for the arrow, we have a collision shape for the area, and we have a homing movement 2D. You can see that the target is not assigned yet because we do that from code when we spawn the arrow, but the speed and the steering force variables are set. And we have this signal connection icon here because to avoid having to code anything for this arrow scene, I just connected the queue-free method to the area entered signal. So what I did, if we take a look at this, is selected the homing movement 2D arrow. It's an area 2D, right? And we have the area entered signal, which has this one parameter of providing the area that we collided with. And I connected it to the same area 2D's queue-free method. But the problem is that queue-free expects 0 arguments and the area entered signal provides 1 argument, which is the area that we entered with. So I checked advanced and I said unbind 1 signal arguments. And what this does is it says that, okay, we know that you provide the area that we collided with, but we don't need it for this connection because queue-free expects 0. A lot of people don't really like connecting signals in the editor like this. I myself prefer doing it from code, but in this case, it made it a bit easier for us because we don't need to attach any code to the area 2D this way. And we have this little telltale sign here that a signal connection is made from the editor. This icon, if we click on it, it activates the signals tab for you, so you can take a look at the signal connections with green. It's just an alternative way to connect signals, right? So that's all the setup we need. And if we go back to this scene and run it, what happens is that the enemy is just wandering around the screen. And if we press space, you'll see that the arrows will spawn at the current direction of the weapon, but steer towards the enemy slowly but surely. And when they collide with it, they just get deleted with queue-free. Now, I've told you that we can take a look at how this works, this transform.x thing. So if we go back to the script tab, press Ctrl+O and search for homing movement 2D under the components, we have this inside already, right? So what we can do is we can comment this out with Ctrl+K. In this way, the velocity will be set to 0 by default. Now, what this does to the code, if I spawn a homing missile, you see it instantly starts turning towards the enemy and it looks really weird. So we want the steering behavior to start from this forward direction that we spawn the arrow from, right? And if you imagine that an arrow is drawn out here and it slowly turns around and starts chasing the enemy, it looks much better and much more organic than just saying that we start from a 0 velocity, and from a 0 velocity, we arrive at the steering behavior much quicker. And we get this angle much faster It might be something that you want. I just wanted to show the difference between the two. Having this means that the base velocity is set to the owner's transform.x, which is the forward direction of the muzzle in this case, multiplied by the speed. So we have this arrow kind of pointing out from the weapon towards that direction based on our speed. And when we press it, it starts moving there, and slowly, based on the steering force, we'll turn around. And you see, if I face the enemy, it doesn't need that long turnaround, right? Because the direction I'm facing coincides with the desired vector that I want to go towards. So it looks natural from all the angles, right? Pretty awesome. And that wraps up our homing movement 2D component. I hope you like this video, and I'll see you in the next one. Bye-bye.